So Karen is principal geoscientist with FrogTech, where she oversees the development of the SEEBASE products. Karen holds a PhD from Monash University and has about 30 years' experience in both the minerals and petroleum industries. Over the past 12 years or so, she's focused on integrated interpretation of potential field data with seismic and other data sets to assess the basement control on basin evolution, the implications for petroleum prospectivity in regions around the globe. Karen's presentation, you can read that for yourself, is focused on the Northwest Queensland region. Welcome, Karen.
Thank you, Tony, and thanks to the Geological Survey for the invitation to come and present the two studies that we finished this year for the government. I personally was working on the Northwest Queensland project. My colleague, let's see if I can get the mouse going. Is it showing up there? Yeah, so Jern did the interpretation at Adavale, so I can't talk about that one in as much detail. Lynn worked with me on Northwest Queensland, and Cedric is our heat flow modeler. Firstly, I do need to acknowledge Santos, Central, and Bengal. These three companies contributed proprietary SEEBASE interpretations to the government studies that would then become part of the public domain. The GSQ team with Justin and a large number of people really helped facilitate the project, get us all the data, and shared their vast knowledge on the area, which really benefited these projects. I think most of you in the room have probably seen this Oz SEEBASE model, and a lot of people will use it as a background to their areas. But I guess I wanted to emphasize today, yes, it is a depth to basement model, and for anybody who's not sure, SEEBASE stands for Structurally Enhanced View of Economic Basement. But there's more behind it. There's a whole workflow that focuses on the importance of understanding the basement so that you can better interpret the overlying basin. So it's an integrated, iterative approach, integrating all the data sets that we can get our hands on. And we're keenly watching what's the developments in machine learning, but at this point it's still hand contoured, and it's that hand contouring that allows us to integrate the subtle variations that we see in some of those different data sets, and also to integrate that structural model into the SEEBASE interpretation. There we go. And there's the extent of the two areas that I'll talk about today. So this is an oblique 3D view looking to the northwest at the Northwest Queensland project. I'll briefly touch on the basement, the controls on the basin, crustal architecture, and then heat flow at the end, and I'll show you some examples from both areas. When I'm talking about Northwest Queensland, I'm going to zoom in, focus on this deep depot center that hasn't got a name, as far as I understand. It's underneath the South Nicholson Basin, and has been highlighted by the recent seismic. And the depth scale you can see there, you've probably got up to about 14 kilometers of sediment in that area. Another oblique view, this time looking to the north at the Adavale Basin. Note the difference in the depth scale, and you can see some of that structural control on the deeper areas, the earlier rift depot centers, and we'll focus a bit on some of the controls in that central southern area. Whenever you're looking at especially a generic SEEBASE surface, or we're talking about that, one of the first things to think about is what is basement. And it's going to vary, you know, it may even vary across a single study, let alone between these two studies. So we're focusing on the petroleum system, so we're talking about economic basement, and hopefully in a lot of areas that coincides with crystalline and magnetic basement. So in this area, so that's largely Devonian age. Yep, my mouse is moving. And the basement underlying that are Neoproterozoic and mainly Cambrian to Ordovician sediments that have been deformed and metamorphosed. And there you can see a summary with the overlying basins, Adavale and Warbin troughs sitting in here in the Devonian. The underlying basement in this area because we didn't have enough data to try and vaguely assess where that metamorphic deformation boundary is between the Warburton, which is still a basin, and the underlying basement beneath the Adavale, which is deformed and metamorphosed. Going up to northwest Queensland, our basin's much older, our basement's much older. In this area specifically, again, we're focused on economic basement, but with companies looking at some of these older units and getting into the even equivalents of the Leichhardt supersequence as we go up into the Northern Territory. It is an important question. So here we're focused again on economic basement, which coincides roughly with magnetic basement. So our main magnetic units, the Eastern Creek Volcanics and the big supersequence in the Calvert. And as when we're in the Leichhardt River fault trough, the Leichhardt supersequence is really thick. As we move to the northwest to the Mount Oxide area, it's thinning. Camargo Dome, it's absent, and up on the Murphy area, the Myalley and Quilala are thinner absent. So if we have SEEBASE basement at the top of the magnetic units in the lower Calvert, that's our economic basement for this study and coincides in some areas with crystalline. Basement terrains, the white boundaries you see up there, I don't want to talk about this in detail, but so regional scale terrain boundaries, and the black dashed lines you can see there are the big province or element boundaries with the Thompson origin where the Adavale Basin sits, truncating that strong northerly trend to the Mount Isa area. As we step to the west, we've got the gravity image on your right. You can see some variation in the trends as we come west into the Tennant area and the Alchiwara terrains, and you can see a strong east-west trend there in those Murphy terrains, and I will come back to that later. So that I'm going to zoom in and talk on this northern area of northwest Queensland. So little location map here, we're looking at the northern area. This is a grayscale magnetic image, and that's the seismic data on top there. So anybody who's been working in the area has probably looked at those seismic lines from the old Comalco survey, and I have an interpretation that we've modified a bit from Bradshaw and Scott on this first line. So the south end of the line here, we have 3 seconds two-way time of essentially the Isa group super basin, and all those units just thin and on lap to the north on the Murphy High. From that study, Bradshaw and Scott documented growth sequences mainly in the river supersequence, and that's dominantly on east-west structures through this area up here. If we step down and now look at one of the deep crustal GA lines, here with an interpretation we've modified that from GSQ. And again, in the oak crop area, we know we have the lower part of the Isa group and the upper part of the Calvert. And as we come to the west, we've got a couple of drill holes here that intersect the lawn. So that means we have the river in between, and we see a nice growth package there. And so that line work and that interpretation, you can see that package thickening to the west. We'll look at another line and come back to that. I stole this image from Paul Henson. So this is one of the new lines, seismic lines from the South Nicholson survey, which came out while we were working on this project. So we had just some preliminary information on this during the project, but not a full interpretation. So you can see this well-developed package of reflectors that, again, that this time is thickening towards the east, as opposed to the west, that we'd interpret to probably be the river again. And if I put that seismic line on that we were just looking at, we can see we've got the river package thickening to the east and to the west into that termite range fault zone, so that you had that northwest trending termite range fault active as an oblique transtensional fault during this time. So with those two relationships, you can put together that structural picture for deposition through that area. Now, I'll just quickly show you one of the other lines. This is SN2 trending northwest here. And again, we can see this package of strong reflectors in the ISA group, exactly where the top is or the base. I'm assuming the interpretation is progressing. And then we see basement a bit deeper down and some significant faults stepping down across this area. So throughout all these lines, you have the ISA package well defined, and then beneath that, you have an older package. It's still clearly sediments, sometimes quite transparent, sometimes with some strong reflective packages in it. But we're quite confident is still sediment. And I haven't got time to go into all the reasoning, but we'd say is most likely to be the early part of the ISA super basin or lake calvert. So we put a gravity model along there and extended it to test that interpretation, and that, you know, we certainly can match the model. We have the broad low of the gravity related to that deeper basin. There's a nice circular anomaly here on the line that we'd say is probably a granite sitting in the basement. We have a broad high in the gravity as we come into this higher density basement to the southeast. Now, one interesting feature here, the deeper moho, that is not from the gravity model, that's from the moho data. So this is the Oz-moho data from Brian Kennett's group. And you can see the points there, and that's just an interpolated grid based on the points. We've massaged that a bit to incorporate the geology into the model, so you can see integrated the basement terranes. But the difficult thing is we see this strong east-west trend in this area where the moho is deep and the crust is and that's at completely right angles to the strong north-south trend of the Mount Isa terranes. So to me, this is one of the most interesting things that came out of this project, because that says something pretty fundamental about what's happening beneath Mount Isa. And we have a terrain boundary which was interpreted independently from the details and the gravity and the mag data, trending east-west between the Tennant and El Jawara terranes, and that's parallel to the east-west trend in these Murphy terranes, which are quite well defined. So I'd say there's an early suture, an early area of crustal thickening that continues beneath those Mount Isa terranes, so that the Mount Isa basement terranes are thin-skinned, they're thrust over top or developed within those basement terranes that sit to the west. And so if we want to understand a bit more about Mount Isa, we need to be looking a bit west towards Tennant Creek as well. So quickly on the Adavale, I'll specifically talk a bit about the magnetic data and some of the results from that for this study. Both images you have here are magnetic data, so the reduction to the pole on the left, a ternary image on the right, which just integrates 3 filters to better enhance some of the subtle features. You can see those 3 broad anomalies that I've highlighted, and there has been a suggestion that those might relate to volcanics in the sedimentary sequence and might be part of the basin. And so that was one of the things that Jern looked at in detail in this area. Now, there's a bit on this slide. We'll start with we've got the location map and the line location in red, and the 2 numbers 1 and 2 on 2 of those anomalies. So that's the location of our model profile across the bottom. So the black line's the SEEBASE, and then we've got the dashed red lines sort of highlighting the top of those magnetic units. So in the northeast, where the Anarchy inlier is near surface or outcropping, we've got a strongly magnetic basement near surface. If we come west beneath the Werben Trough, you can see those magnetic units are really quite deep, and we have a non-magnetic or very weakly magnetic unit at the top of basement. And coming beneath the main Adavale, similarly, we've got some magnetic model bodies there, but they're really low susceptibility. So we have an upper basement unit that is those Canberra-Ordovician metasediments that are very weakly magnetic, and then those big broad anomalies are more consistently modeling down in the middle of the crust. And with this oblique 3D view, you can see there's a large number of those bodies across through there. So we'd argue those are basement anomalies and coming from the middle basement. And just looking at this model to this anomaly to the southeast, Jern referred to that area as the Westburn block. Interestingly, it's quite distinct and it coincides with the zone where the moho gets deepest, where the crust gets thickest. So again, these points are the moho points, and I've just labeled the shallow one there and the deep one down here. So we'd argue that there's a distinct crustal block, not necessarily a full terrain, but it is an area of more competent crust and thicker crust that is then controlling development of the overlying basin. So we'd say this block would probably extend to the southeast beneath these shallower magnetic units. A 3D image that Jern put together, so you can see the moho surface getting deeper here beneath that block and the position there. So it's probably one of the features controlling development of that early Sin Rift phase. I'll just very briefly touch on our heat flow, our approach to basement heat flow and understanding basement heat flow. So we start with our understanding of basement, looking at the basement terrains, and then we take that a step further and interpret the basement composition. And the key, two key reasons we do that is to better understand the variation in rheology of that underlying basement, because things like big granites are going to be more competent. But the other thing, they're going to be more radiogenic. So we then look at, if we've got a general analysis of basement composition, we can apply heat production values and look at basement heat flow. So those are the heat flow data points that we could pull together, or Cedric could pull together for this study. And that's just an interpolated grid that's, those heat flow points have been gridded and then smoothed. In contrast, when you start thinking about what you can say about the basement composition, you can come up with a geologically constrained model of basement heat flow through those areas where you don't have information. So that incorporates that interpretation of basement composition, crustal thickness, and an assessment of the radiogenic thickness of the crust. And Cedric, because there's so much data on the composition of the outcropping geology, he used that to actually constrain the heat production values for this area. So that's a good starting point for your basement heat flow for any thermal modeling. So the key point that I started with that I'd like to leave you with today is that with the next time you look at a SEEBASE depth to basement map, remember that there's more to it. There's a whole study behind it that's focused on understanding the basement and then being able to be more predictive about the basin evolution, the depth to basement, and the basement heat flow. And we're focusing on Queensland, but I will just say there's studies, the states have gotten involved in doing some updates across Northern Australia. There's separate reports on both areas and a full GIS package that's available from GSQ. Thank you.